there resources you recommend for learning more about VHDL?
Yeah, so I could post those. I actually don't like most of the VHDL online resources for a couple of reasons, but really the way to do it is just practice. So this project is actually really good because you built this lab rather. The lab 5, right, was a really good lab because you've already built something by hand that represents the hardware that you're designing. So when you go and you write out your K-map for a full ladder, right? So you have something. Only that one. That looked like that, right? That was your K-map, and each one of them circled, and you're looking, and you end up with a device called full ladder. And it has ports A, B, C in, some CFs, right? And I've provided you the entity for this one. So you already know how it's supposed to connect to the outside world. That's all the entity is doing for you. It's describing how does the outside world see this block. The outside world doesn't have to know what's inside of it. It just has to know what it's supposed to do, which is add. And so when we do this, we're going to design just a full adder, which is going to have a carry in, right? And hopefully most of you have your full adder built and tested by this point, because it's as simple as saying, well, the carry out, right? Its A-map was ends up like that or something. And all it's saying is when you circle it is that in an adder, if you have any 2 inputs that are ones, I get a carry, right? Because that's just the definition of an addition in binary. 1 + 1 is 0 with a carry. Doesn't matter if this is A and B, or B and C in, or A and C in, or all 3 of them. So you have this expression, CO gets assigned to, right? This is an assignment statement that we're going to get back to thinking about, and say it is A or B. Sorry, A and B. A, B. But if we're in the HDL, we need the and, right? A and B, or B and C in, or the other one, right? A and C in. And if I write that, I'm done. I've designed the carry out circuit for my full adder. I do the same thing for the sum circuit, right? There's 2 different circuits inside of this full adder, just like you built 2 different circuits inside of the previous lab. Then it's just a matter of taking these. And if I want to turn this into the 2-bit adder, right? This is hopefully I'll review for everyone. I take another instance, right? So the entity is declaring how it interacts with the world. Then you make a component declaration, where the component declaration goes in between the architecture and its begin, right? This is where we say things exist. So here is my component declaration. The component declaration, again, the way to do this, always, 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 is just go to your entity, which is its own design file, right? You copy the entity, you paste it over here, and you change the word entity to component and change the word end from end entity to end component, right? We're just adding component in 2 places, and that copy and paste says this exists. And then it's a matter of saying, well, now I need to pull this out of the bin. I said I've gotten the bin out of parts. Now I need to start pulling parts out of the bin. So the first one is I give it a name. That's what goes first. This is my 0th full adder. This is a component name, not what type of component is it, What's the name of it? Its type, in this case, is FA. It's full adder. This would correspond to something that would be entity FA is, and then describe its ports. And then I give it a port map. The port map is just saying, well, my component declaration has told me that there's A, B, C, N, S, and CO. It's told me what ports there are. Now I need to name the signals that are attached to it, right? Well, let's suppose that in my declaration, I have that full adder. And so I'm going to have A gets mapped to something, right? So this is just the reverse. This is how I say it. A gets mapped to something. What am I getting mapped to? Well, if I'm building a 2-bit adder, then what I'm going to have is this type of structure where this is A at 0, B at 0, A at 1. Oh, sorry, I didn't do this the right way. 1, 1, 1, 0, B 0, CN, S, CO. This is going to be some at 0, right? The parentheses are saying that I've created a standard logic vector, which a standard logic vector is just a vector of standard logic bits, right? It has more than one in it. And so what I'm going to do here is just walk through again, because having this rehashed is never a bad thing, because this is where people are still struggling to get. And once you understand this, you're pretty much good for a good chunk of the difficulties of the class. But then we have to look at this and say, well, that makes this S at 1, and this, we can do 2 different ways. We can either call this the carry out, or we can call this sum at 3. This works if I'm using a 2-bit adder, right? If I do anything else, then I need to just treat this as a carry out the same way as here. The reason this works, right, is an addition looks like this. So I have A, which is a vector of 2 bits, plus B, which is a vector of 2 bits, that gets a sum of 3 bits, because I can potentially have a carry out. Well, the only thing then that's left is there is this signal, right? And my signals have to have a name. I keep harping on this because it's really important. CO. I could just call this C at this point in time. There's nothing else that's just C. I could call it carry, whatever I want. And that's going to go here, right? Because that's the carry out from this addition. So if this is here, 1, 1, 1, 0, and I do this addition, then the first full adder is going to add those 2 together, which is 0. So that means C is 0. Then it adds 1 plus 1, because A at 1 is 1, and B at 1 is 1. So then it's 1, 0, 0. That would be my sum. Similarly, yeah, 1, 0, 1, sorry. Let's say I have this addition. Now it's 0 with a carry. That carry is now 1, which the carry in sees. And now it does 1 plus 1, which is 0 with carry. Right? That's all this is doing. You just write the code one time. But there is a caveat, which is if I want to use this 2-bit adder, like so. It's its own component now, right? Which it's going to use other smaller components in a hierarchical design. It's just going to call, I need 2 of these guys in order to build a 2-bit adder. That's what this larger one is going to be called. Okay, but when I do that, I don't want to tie this carry in directly to ground inside of the 2-bit adder. Because what I can do is if I have a 2-bit adder, and a 2-bit adder, then I can make them, sorry, I'll be down here. I can have them work together, and now I have a 4-bit adder, which is really nice, where my A and B inputs now are vectors that are 2 bits long. If I tie it to ground inside of the component, then it can never be anything but 0, which is a problem because then when this carry in is supposed to be 1, inside it's actually tied to ground and it's stuck to 0. So we don't want to do that until the port map, right? Because I don't have a C here. There's no carry in here. This is always going to be 0. So what I do is I say, well, my first full adder, A, gets mapped to the first bit of its input vector A. B gets mapped to B at 0. Cn, again, this is FA0, which is the leftmost one, gets mapped to 0. Now I've tied it to ground, which I've done. Well, that works if I'm trying to stop at the 2-bit adder, if I'm done. If not, then I want a port called Cn. Now I can use this 2-bit adder as a component in a 4-bit adder. Do you see the difference? Is this one is going to have ports A, B, their standard logic vectors of 2 down to 0, and Cn, which is just standard logic, which doesn't have a vector, so it doesn't need to size. Oh, sorry, not 2 down to 0, 1 down to 0, right? Because it's 2 in size or 0 indexed. Okay, so there we go. I would also need the output ports, right? But let's just focus here. And then I have the Cn, which is getting mapped to that Cn, which is getting mapped to this Cn, which is really the component level Cn, right? So now I then can say, well, my remaining ports are sum, which can get mapped to, well, that sum is the first one, which is S at 0, and C out gets mapped to, we call it C. That C doesn't exist, so I have to go make it. Signal C is standard logic. It's fine to go back and create things after you realize you need them. I do that all the time. I go, oh, where does this go? It gets C, that's C. It's very important that we be able to look at pictures and turn it into code. This is very important because this is generally how we're going to think about digital design. Then I need to do something with the second full letter, FA1. Of course, if I were on a computer and had not forgotten my laptop on the day, I would just copy this whole thing. I would paste it down here, and then I would just rename it from 0 to 1, right? These are the unique names. This is the instance name. This is the component that I'm using, which is just FA. It needs its port map. Its A gets mapped to A at 1, right? That's just what I drew. B gets mapped to B at 1. Cn gets mapped to C. What this is saying now is this output port C0 is connected to C on one end, and Cn is connected to C on the other end. This is what makes that connection for me. Everyone get that? Make sense? Then it's just a matter of S gets mapped to S at 1, and CO gets mapped to, well, now this carry out depends how I've decided to define it. Did I decide that this is S of 2, or did I just declare this as CO of my port? Either one is fine. I think in the ones that I did it as its own port. So let's stick there, CO. And we just have to remember that this is kind of a worst case scenario, right? Because I've actually used CO and CO as the same port names, which is okay. Because all that's saying is that my port for full adder is CO, and then the port level, let me do this real quick. Here is also called CO. I have a port called CO, I have a signal called CO, and then a port called CO going to that. It's just the same thing called a bunch of different things that are called the same thing and then are connected together. So we need to keep track of these kind of hierarchical port connections in our minds, and it's okay to use longer port names if it helps you, right? I could call that CO underscore 2B for the 2-bit. Well, my 2-bit adder's done because I've mapped all of my ports. They're doing all that's functioning. Hopefully, as I step through all options of A, B, and C in, then I will get the expected sums, which I viewed through that waveform viewer, right? The simulation window. And we just look at it as a, I'm just gonna drop here. So like our A's are going to look like this. So this is A. This is B. And this is not, of course, in order. Maybe I'll just do it this way. Right? Our signals, our input signals might look like this. Now, A is represented by default in hexadecimal. So I need to look, is 1 plus 1 plus 0, does it output into my sum the expected value? So down here, my sum would hopefully be that, well, 1 plus 1 is 0, 1, so it should be 1 plus 1, 2. And then at this point in time, it changes. My A changes. That's what that's showing me. That's a transition from, I'm changing A from 1 to 2, right? I did that in my test bench. I would have told it to do that after some amount of wait. We have that example kind of built up test bench. And then, well, once I have 2 plus 1, it's now 3, which is 1, 1. That's allowed to be represented in a 2-bit sum. 3. That's fine. If, well, this is 2 bits, A is 2 bits, right? If this then becomes 3, and this stays 1, well, now I have 3 plus 1, which is 4, which is too big to be represented in 2 bits. So 4 is represented as 1, 0, 0, right? That's 4. So my sum here becomes 0. Because sum is only 2 bits, right? It's 0 and 1. But what we will see is that the carry out value will be 1. So the sum is 0, 0, 0, 0, but the carry out bit becomes 1. And I have 1, 0, 0, the number is 4. I've written the test bench for you that will test that and make sure that it works. Of course, in yours, you have 2 different ways of doing the design, right, for the lab, which the easiest way is I just add another FA2 and FA3 and call it a 4-bit adder. making sure that I have 3 signals that connect between, so I'd have like C0, C1, C2 to connect the 3 full adders together, and then I have that final carry out, right? Any questions on that? Okay. Other way is I could call this is my now 2-bit adder. I save its components. I create a new design file, right? A new design source using Vivado. And then I would declare a new component called 2-bit adder. And then I would use 2 of those to build a 4-bit adder. Right? This is the hierarchical design that we kind of want to focus on in order to make sure that we're understanding the building blocks for everything that we're going to do from kind of here on out. Well, not everything. We are still going to do some other topics, but if we don't understand this, everything gets kind of difficult, if I'm honest. Okay. So the other thing that's on today's lecture is first off Muxes, right? But we've talked about Muxes. But there is a nice cool thing that we can do with Muxes is we could just write the logic, right? Where we said that this is what a mux looks like. It has a select signal and 2 inputs, A and B. And when select is 0, it takes A. When select is 1, it takes B and puts it in its output. And then hopefully you could go and draw a truth table for that, then write the logic. However, there's a really nice bit of VHDL code that we would just call a select statement. And I'm just going to pull it up to make sure that I get it syntactically correct, since I don't have a laptop. This computer does not have Vivado, so I have to handwrite it all, unfortunately, and I don't have my laptop with me.
Just download it on the computer. It'll only take like all class period.
Yeah. So sorry, this is going to be, I don't want to use that one. So let's say I call this output M, so I've done before. So I could either do a 3 input truth table with S, A, and B, or I can do what's called a select statement. Now I don't usually actually use the select statement that often. Instead, I usually use what are when else's. But let's start with the with select. So if I do this one wrong, I'm sorry, because I almost never use this. So with S, we're going to select M. And then we ask the question, what is M getting assigned to? Well, now it's just, see this port? We're going to call it A. A. It's going to get A when, what is S? Well, S needs to be 0. And in this case, 0 is actually a bit. So we have little apostrophes. Then we say comma, E when 1. Done. I built a mux. Right? However, this has a huge advantage over the 3 input truth table, which is if I want to build a 4 input mux, I don't have to go back to the truth table and write the logic. I just extend S to be a vector and I make it more rows. And I'm going to do that with something slightly different, which is the when else statement, which is the easier way to do the same thing. So what a when else says is Well, let's just go ahead and call M gets assigned to something when S. So let's say that I have a 2-bit mux. Or rather, a mux that wants to select between X, actually, let's keep going, X, Y, W, X, Y, Z. Well, let's say that each of my inputs here are 4 bits. I want a 4-bit signal. That makes my output 4 bits. How many bits does select need to be? Just 2, because this would be 0, 0, 0, 1, 1, 0, 1, 1. Right, 2 bits, 4 choices. So for the select, we want to look at how many choices do we have and what's the fewest number of bits. Now, there is something worth mentioning, which is there's a thing called one-hot encoding where we will do exactly what you just suggested, which originally I was going to talk about encoders today, but I think I'm going to skip that for now so that we can kind of focus on this lab and we have an upcoming project to get started. Well, let's say we want to build this. But that means when I've declared the signal M, I needed to make it a 3 down to 0 vector, right? And this is M 3 down to 0. Now it's a 4-bit vector, matches my picture. Well, now I say that B, or rather, well, M, sorry, M gets assigned to W when S is equal to, well, I need quotation marks now because bits use apostrophes, vectors use quotes. Else, W, X, when S equals, so quotes like this, if you're not familiar, just mean copy the line directly above it. 0, 1. Else, Y, when S equals 1, 0. Else, Z, when S equals 1, 1. Now, if I leave it as is, I'm actually okay. Because these 4 whens, else, I just end. And now it's else this. There is, however, one problem with this, which is kind of not obvious, which is this is what happens when S is 0, 0. If I build my test bench and I start stepping through all possible combinations to check it, and I accidentally wire it up wrong, and my select signal is instead UU, right? Because U is a valid value for a standard logic. If UU, what is M? It's actually Z. Because it takes X when S is 0, 0, or W 0, 0, X 0, 1, Y 1, 0, otherwise Z. So no matter what, if I do something wrong, something weird, and put my select in as anything UN S. Oh, else, I guess, sorry, I did a little bit too much. Else Z is technically all I need to do. Because this is the else statement. Now, I kind of screwed this up because if I do have the when 1, 1 and no else, I'm actually okay. The issue becomes I really want an else, something useful that would tell me that I've done something wrong. So maybe, right, X's are allowed. Now, if I put select as anything that isn't a useful number, right, one of the selects, my output of mux is going to be X's. And that's a useful debugging tool because now when I look at the waveform, I go, oh, something must be wrong with my select signal. Otherwise, I could fall into this trap of what is it actually doing, whereas this can be helpful. There are anything that you put here is actually really helpful. You could even do something like DZ, right? Z's are high impedance, meaning it turns off. So if you don't select something, it's off, it's disconnected, which is fine. Which you would draw as having an output enabled buffer, right? Which we talked about right before the exam. This device. Which just says turn on or off the output. Get comfortable using these when else's as muxes because they're incredibly useful because it's just one line per input and then one extra to handle in case you connect it wrong. So coming up on Thursday, I'm going to hand back the exam. I've already posted the grades for everyone as well as the statistics. The exams are just sitting at home with my laptop at the moment, so I can't really give them back to you right now. So anyways, I posted the statistics for it overall. You guys did really surprisingly well as the majority of you. If you're unhappy with your grade, you need to talk to me and we'll figure out what you don't understand, right? Because that's all it was, is I think the high score I think was 98 or something. There wasn't a single problem that every person missed. So at least one person got everyone right. There were a couple of problems that everybody got right, which is a good sign, because those were like some of the really important ones. The ones that were frequently wrong, actually, that missed a lot of points were K-maps, which were confusion between the sum of product and product of sums and which equations went with them. And what that tells me is that you probably didn't go back and look at the solutions to the homework that I posted and correlate them to your own, right? Because that's going to be one of the big challenges that you're going to run into here at the college level, is you do need to do some of your own self-reflection. You need to go back and look at your homework and say, what did I do wrong? I can provide you the answers, but I can't make you read them. I can give you feedback on your labs, but I can't make you care about them, right? The labs, if you're missing points on labs, you're just missing bullet points, right? That tell you where the points come from. So I want you all to succeed. No matter how terrible you did on this exam, you have not failed the class. That exam, the midterms are only are 20% a piece. So even if you fail that exam, right? If you get 50% on the exam, then you've missed 5% of the overall grade is all. It's just not that much. What you do need to worry about is getting back on track, because K-maps aren't going away, right? This kind of design process isn't going away. We're just building on top of it. It's not all of the grade. It's going to become a lot of VHDL, but there's still going to be some of that design. So don't panic, don't freak out. You're still doing, every single person in this class scored high enough on this exam that they're still in a good place to pass this class. In fact, everybody did well enough on the exam that it's still possible for everyone to get a B or better in this class. We just need to make sure you're doing okay. So don't be afraid of coming and talking to me so that we can help push you on the right path so that you guys can succeed. Of course, you'll want to talk more after I give you the exam back and you can look over and see what you missed. And of course, check it, right? I'm not perfect and there's a lot of exams that I have to grade. So when you get it back, go make sure that everything is, that I marked wrong is actually wrong, because it's possible that I screwed up. In fact, I know that I screwed some up and I went back and fixed them, but hopefully that doesn't, hopefully I fixed them all, but I'm not going to promise that I did. Okay. That's just about a little past halfway, I guess, through class. So I'm gonna run downstairs and make sure that that lab is open, and then I'll be right back, because if we can, how many of you have tested your full adder at least? So almost all of you. How many have tested, at least tried to simulate the 4-bit adder? Okay, so we're up to about half. Great. So our target, because next week we need to start a project. We're actually going to start our first project. Actually, I'm looking at the schedule to see if
It's Thursday.
yeah, it's Thursday that's going to start the project. You know, I'm just going to use this as a chance to introduce the project, because we've already talked about a bunch of this stuff that's going to be relevant to the project. Because it turns out the project is just going to build on this lab, what you know about this lab. Okay, you kind of need the you need this lab in order to build the project. They kind of link together, as a lot of stuff coming up will. I strongly recommend not falling behind on labs if you can avoid it at this point. It gets harder. So what we're going to build for our first project is going to be an ALU. And it's going to be an 8-bit ALU. Now what an ALU is an arithmetic logic unit. Now the arithmetic logic unit is pretty simple. So I'm going to draw this really big so we make sure I don't run out of space. Okay. So an ALU is going to look like this with an input A. Actually, I'm going to put the ports on the inside first. And it's going to be 8 bits. And we're going to have B, which is also going to be 8 bits. Then it's going to have what we're going to call your opcode. And all that is what function would you like it to do? What do you want it to do? So you'll notice that this looks a fair bit like a mux, right? Well, what it's going to do is first off, it's going to have an adder in it, but it's going to be an 8-bit adder, okay? Which is easy once you finish your 4-bit adder, right? You just stick 2 4-bit adders together and you're done, as long as you don't tie your first one to ground. If you tie your first 4-bit adder to ground inside of the 4-bit adder, it won't work to stitch them together. Otherwise, it's pretty easy. What it's going to do is it's going to be add A plus B. We're going to build a subtractor. The subtractor is actually walked through in the book. It's not very difficult. There's a bunch of different ways that you can implement it. I actually don't care how you end up building this subtractor. You're just going to build it, test it. Should be okay. It's going to look at B and A and give it a result. Then, sorry, there's going to be a couple other functions, or one other function I think that we'll get into. Then we're going to build something called load. And something called hold. These are going to set up because we're going to need them later. Because later what we're going to do is we're actually going to use this as kind of the brain, essentially, the computational unit for a calculator that we're going to put onto our FPGA. So we're going to build an FPGA based calculator. Now, our calculator, I have to decide, we're going to build this 8 bits at first. Our board only has enough switches for 8 bits because there's only 16 total switches. So I may come back and have to revisit how many bits we're using in these when I get to final calculator to put it on the board, but that's a problem we'll deal with later. Right now it's 8 bits. It's not that, right? It's not really any more difficult to build 8 bits than it is 4. It's a couple extra copy and pastes. Then the output here needs to look at the opcode and say, what am I going to do? Which operation do I care about? Well, it turns out that's going to be a mux. So the opcode comes in, tells the mux, which one to choose. So it turns out that the ALU is doing too much work, right? In a way, is that it's doing the addition, subtraction, the load, hold all at the same time and making each of those results available to the mux. And then the opcode is just going to say, which one do I want? Now, these opcodes are kind of interesting because we could think of them as a list. Well, let's say we're only using these 4. How big does my opcode need to be? 2 bits. Yeah, right? Because 4 inputs, 2 bits. Well, if I have a 5th one, now I need 3 bits, and some of the opcodes might not get used. So then I could say something like, well, when opcode is 0, 0, then I need to add. So that's function, right? Opcode is 0, 0, that's its function. 0, 1, subtract, 1, 0, load, 1, 1, hold. But we're people, right? And we can have a hard time remembering what all those numbers are. So what we can do is there's a thing called constants. Constants are really quite wonderful because what constants do is now I can say something like op add. Now, if I write the constant correctly, which I'll show you, when I write the words op add, then it will know, the VHDL will know that I really mean 0, 0. But I don't have to remember that 0, 0 means add. We do constants very similar to how we do signals. The difference between the constant and the signal is that the constants don't change, right? Signals carry values. Constants just carry, well, signals carry signals that change. Constants carry a value that's fixed. And we can use it throughout to keep our code organized. That's its main function, is to organize our code to be human readable. So if I were to want a constant over in this code, I would say constant, okay? Just like signal, give it a name, op add, and then just like the signals, right? I need to make sure that I know what it is. What type is it? What's the data type? And this is, well, op add is going to be a standard logic vector of size 1 down to 0, right? Now, standard logic vector, SLV, that's the abbreviation that I use when I write on the whiteboard. You can Google it if you're not quite sure what the right actual syntax is. Well, I'm not quite done, because how do I make op add have a value? Well, I do this where I say colon equals 0, 0. Ta-da. Now when I write op add, it does 0, 0. Now, where this is useful is if you guys build your internal ALU different than I do, say you have add as the second spot. As long as your op codes are in the right spot and I say op add, your ALU will output the right value, right? It's just creating a map between op add, the op code, and what the function is supposed to do. So here I would treat op sub, op load, op hold. I would write 4 lines of constants. This colon equals sets default value. One word of warning that is very important to be aware of is this works wonderfully for constants. This does not work very well for signals. And it's easy to get fooled because if I were to do this for a signal here, signal C is standard logic. I'm allowed to type this 0, 0 is standard logic 0. Okay, that's saying I want this signal to start at 0. Well, the issue is twofold. One, in your simulation, if signal C is not getting assigned to something, we would like it to be undefined because we didn't connect it right. But because I've declared this, it will be 0. And I'll think, oh, why is it stuck at 0? Well, because nothing else told it to change. The other issue is that when we take this code and we put it onto an FPGA, this doesn't come with it on a signal. That default value doesn't synthesize, is what it's called. So signals, we don't like to do this. You are going to be tempted to make your simulations work, but if you need this to make your simulation work, then your code doesn't actually work. Okay. Constants, however, function a little bit differently in that since it doesn't have to carry a value with it anywhere, it doesn't have to change, it just loads this value into a memory location. It says, puts it here, and anytime I want that value or give it the word op add, it goes and looks up what are the contents of that memory location, and that never changes. So that's why it works for constants and doesn't really for signals. So just be aware. This initial value statement, save it for constants. Stay away from signals. Of course, there's going to be exceptions later, right? Any rule I give you, you're probably going to end up running into exceptions later, but for now, it's going to be easiest to just not do that. So once I have those constants, op add to op hold, the Mux will choose which value it needs, put it at the output, project one's done. The whole trick of this is being able to look at a picture like so and turn it into code, right? You're going to write 4 different sources. One of them is going to do 8-bit addition, one of them is 8-bit subtraction, one of them is load, one of them is hold. You're going to build a mux using when else, just like I showed you. It's going to take the outputs here. These each need to be their own intermediate signal names, right? Because they don't leave the ALU. I have to declare them as signals. They need to be the right size. And if I'm adding 2 8-bit numbers together, how many bits is this going to be? If I add 2-bit numbers together, how many bits is my sum? 3 bits. So if I add 2 8-bit numbers together, how many bits is my sum? 9. Right? Because it's just that's the biggest number I can add together. 1, 1, 1, 1, 1, 1. Sorry, 1 plus 1 is 0, 1, 1, 1. Right, 9-bit number. 2 odds make an even. Easy check. That's all this is going to do. It's going to have a 9-bit result. That means our output is going to be 9 bits. Well, eventually we're gonna have to switch this up a little bit, but this will work for now. So now you're looking at a potential 9-bit. There's only one little bit of an issue, which is load is going to come from B and hold is going to come from A. And then we are also actually going to have carry in. So, for example, the hold, which is going to take A, it's going to just take whatever the carry in is, which is there's 8 bits here, there's 1 bit here, there needs to be 9 bits here in order for everything to make sense. So it's going to take the carry in and A and merge them into one vector. Okay, we're going to mix them together. It turns out that's really easy. If I have a signal A and Cn and I want to stick them together, so if I call this signal, I'm just going to give it alpha so I don't mix it with anything else. Alpha gets assigned to that. A ampersand Cn. Ampersand concatenates is the word, which means take two things, stick them together. In that case, alpha is 9 bits, A is 8, Cn is 1, 8 plus 1 is 9. This is fine. It will concatenate just fine. Probably that's going to stick Cn on the end of A. I probably want to go the other way, but we'd have to want to think about it a little bit. Anyways, that's an ALU. You're going to write a couple different components. You're going to write a top level module called ALU. You're going to declare these components inside of them, right? Hierarchically. Inside of this might be the full adders that you've already added, or 2 4-bit adders. So it's going to have a couple layers of hierarchy. And then connect them up with named signals, right? So like the port map of plus, if this is X and this is Y, then X is getting mapped to A, Y is getting mapped to B. If I also call this X and this Y, same thing, X gets mapped to A, Y gets mapped to B. It's okay for multiple things to take the same signals as inputs. It is not okay for multiple signals to drive the same output. Does that make sense? So I can have A. X is an input here. This X is an input. In fact, to change this up, X, Y, F, G. Well, I don't want to call it L. I was about to. Okay, there we go. Okay, and Z is not used. Okay, so I'm going to declare these components. I'm going to say they exist over here in the architecture before the begin of the ALU. Then when I do my port maps, my instantiations, then my adder, let me just erase a bunch of this. So this is going to be the entity ALU who has ports A, B, which are 7 down to zeros, Cn, which is sorry, that needs to be standard logic vector, but I'm not gonna put it. This is just standard logic, and out, I haven't named it anything. Let's call it R for results, which is a standard logic vector that is going to be 8 down to 0, because that's how big the result is. That's R. it's 9 bits. 8 down to 0 is 9 bits. Okay. It also needs opcode, which is a standard logic vector of 1 down to 0. Then I have the architecture. Here, I'm going to need to say, well, my components exist, so I'm going to be something like component add 8. And it's going to be the copy and paste of the entity, but for the adder instead, right? And it's going to have is or something, ports, X, Y, and so on. Then I'm going to need another component, sub 8 is, fill in its value. All I have to fill it in, right, is just copy and paste. Then I'm going to have the begin of the architecture, and I'm going to have the adder. Oh. It needs a name first, right? That's the first thing in the instantiations. So call it add 0 is a component of add 8 whose port map is, well, it has a port X that's getting mapped to A. A is 8 bits, X is 8 bits. I'm good. Fill in the rest of the port map, then I'm going to have sub 0, which is sub 8 with a port map, not X. Yes.
When did add 8 and sub 8 like get defined?
I would have had to call them here. That's add 8.
Is that different than the OP add? Like when we
Correct. Yeah. So this, each one of these blocks is its own design source that does the associated function. The opcode is just saying which of the outputs of each of those design sources do I look at. So for example, if this, so this one I called alpha, so X, Y, F, G, A, B, let's call this E. Okay, so this output E, if I choose opcode opadd, it puts a 0, 0 into the mux, it takes E and puts it onto R. And then that's its new output. It takes the adder. F, G, H, call this I. Similarly, if I choose op sub, opcode then will be 0, 1. It puts 0, 1 onto this mux. It takes I, puts I into R. There we go. The subtraction is going to be kind of an interesting one that I need to change the lab write-up for, because right now the current lab write-up doesn't have the subtractor in it. We want to be able to subtract numbers, but we're going to have an issue of if we want to subtract 2 numbers and be able to go negative, we need to store everything as 2's complement, right? Or sign one or the other. So I have to rewrite the project to make it clear how you're going to implement that part. That might be the trickiest part, other than just connecting them together. So back to the original point, see how I've mapped A and A to the same thing? This is okay because these are inputs. So it's just saying that one signal can tell multiple things what to do. Just like a traffic light is an output and it can tell multiple cars that it's okay to go. However, if you have 2 signals trying to drive the same thing, it doesn't work. So if you had one stoplight or 2 different stoplights facing all of those cars, and one of them was red and one of them was green, what is it? Right? That's the issue. So all that's saying is, as I fill out the rest of my port maps and I finally get to the outputs, I'm just going to start using O, 0, O, 1, O2. So here I'm O0 gets mapped to E. If I accidentally say, well, here, this is O1 gets mapped to E, now I have a problem because both of those are outputs telling E what to be, which is very different than a signal telling the inputs what to be, right? This is okay, that's not. In code, it doesn't look as obvious, right? Unless you understand what the outputs are. To that end, sometimes people find it useful rather than calling it O1, for example, and leaving it there. I mean, O1 is kind of always out. Adding underscore O. E is a signal. So E would be underscore S. A is an input, A underscore I. May help you. If you have a hard time keeping track of what your signals, inputs, outputs are doing, add the underscores, output, signals, inputs to keep track. Okay, make sense? All right, so we're about out of time here for class. What I want to see is I want everybody to be attempting to simulate the 4-bit adder by the beginning of lab. Because the way that this is going to have to work out, right, we're a little bit behind, which is okay. COVID semesters are going to do that. So what we're going to do is be trying to test your 4-bit adder. If it's not working, that's okay. During lab, I will help you figure that out. But between now and Thursday, I need you to get to the point where you're trying to test it, where the simulation is running. Remember that if the simulation is running, I've told most of you this, I've said it in front of the class, but it is worth repeating. When trying to figure out what is wrong with your code, the TCL console, which is near the bottom of Vivado, is your friend. Okay, it's going to have like a little tab that goes up above it, and when you click on it, it's going to bring up a window that's going to have a bunch of code. I wish I had the appropriate colors, because what's going to happen, you're going to pretend that this is red, okay, is when you first see it, there's going to be like error. There's usually at least 3 errors when you mess something up. So this is what's happening if it doesn't run, okay? If it doesn't run, if your code is failing, it's going to have some errors. These are going to be in red. What you want to do is scroll up until you see the same number of errors in black. And in fact, they correspond directly to each other. The difference being the one in black is actually useful. It actually gives you more information than the one in red. It only takes a little bit of scrolling. There's usually just a little bit of text in between the black and the red errors. But go find your first black error, scroll up to it, and at the very end, as you read across, well, here it's going to tell you what the error is. It's going to be like your signal sizes don't match because you tried to plug a 3-bit vector into a 4-bit vector, or a standard logic into a standard logic vector, right? The types don't match. Whatever the error happens to be, then later it's actually going to tell you the file and the line number. So you'll find the first black error, scroll to the end, you will find the exact line errors. Start with the first error, fix that one, and then move on down, then rerun it and move on down, unless it's obvious that you can fix all of them, right? Because errors beget errors, right? Fix the first one so that you actually know what's the problem. Also, the nice thing is once you have your test bench up and running for the 8-bit adder, the code that I've provided for you that runs through and tests all possible input combinations will also here, if you don't have any issues, will be blank. The TCL console won't do anything. If you do have errors, it will say something like error colon bad sum. If you don't see any error bad sums and no other errors, probably works. You're probably good to go. You'll want to go check a couple of the waveforms and make sure that it's adding in the way that you think it's doing, right? Because that's all this is doing, it's adding. Once that's done, then you're good to go. Make sense? Worth noting right before we go, in the subtractor, when we get there, you don't have to build a full subtractor. You can literally just write a subtract b as long as you do it right. I'm totally okay with that, okay? The main part of this project is getting you used to building slightly more complicated circuits. That's all for today. We'll get your exams back to you on Thursday.
You're gonna meet in the lab next Thursday for class. So
Watch your announcements. I'll figure that out.